All right, it's a pleasure for us to have Dmitri Burago today from Penn State. Take it on, please go.
Okay, so I'm going to start with a rather naive question. I don't know who exactly formulated this question. I think that some version of it goes back to Erdős, but in a different formulation. And of course, the approach here is also different from probably Erdős would expect. And this is joint work with Sergei Ivanov, which is completely unfinished in the sense that there is a theorem, and you will see that the theorem is not quite satisfactory in a sense. However, there are plenty of open questions. And basically, I'm going to concentrate more on open problems than on theorems in my lecture. I mean, of course, open questions without any theorems sound like, okay, a stupid person can ask infinitely many questions. But for a good question, scientific advisor of my mother, famous Linik, would say that giving someone a problem is like buying a new suit and giving it and say, wear it. So giving out a problem is more important. That when you solve a problem, you kill it. And so you take away something from people. So here we semi-kill the problem, and then you'll see if you can kill it completely. So I need the following naive definition. So here is, do you see my screen? I guess you do. Definition, what a metric graph. So what is a metric graph? A metric graph is just a graph such that for each edge, it's a non-oriented graph, and for each edge, we attach a positive or non-negative number, which is its length, well, let's say positive number. And so what we want is uniformly bounded in the sense that degrees of vertices, it's going to be an infinite graph. All degrees of vertices are bounded, and lengths of edges are between two positive constants. It does not really matter what would be the constants. And for the degree, you always can just simply say that the degree is less than 3, and that's enough. Because whenever you have a vertex with degree 4, you can transform it into two vertices with degree 3 by adding a little edge. And you will see that for our problems, that wouldn't matter. And the same as with lengths of edges, if edges are bounded between, you want them to be bounded between 1 and 100, and you see the edge of length 1000, you just add vertices along the edge. And so specific values of this constant do not matter. And so here is a general definition. You have a metric space, and you say it's uniformly approximable. So you have a metric space X with a metric D, and then there is a graph gamma, metric graph. And then there is a distance function on this graph. So gamma here is a metric graph. I mean, things are typed, but I know when you show a picture, people perceive this as a picture. When I write, they have to follow what I'm saying. So I still write things again, and then they are within finite Gromov-Hausdorff distance. So I want to replace my object, which is logical, continuous, whatever it is, by a really discrete model of controllable local complexity. So no large degrees, no long and no very short edges. So locally, everything is very finite with uniform bounds on the whole story. Now, to make clear that it is not too abstract, you always can choose vertices. So gamma has vertices and edges, right? And then functions, some function distance from edges to non-negative numbers. It's what is our graph is here. And we choose V to be a subset in a natural way of X. Forming a separated net. It's an easy exercise that if you have such a graph, then you can make a correspondence between vertices. And so, as a matter of fact, if you rephrase it in more down-to-earth language, this means that you have your space X. It has its distance function D. Now you choose a bunch of points here inside this thing. You connect them by abstract edges. So edges, of course, are not in X, they are abstract edges. For each edge, you assign its length, L of E. And then you get another distance, which is the shortest path in the graph. So you get some distance between points in the graph. And so what you want to have is that this distance measured inside the graph differs from the actual distance. So let me just write it down. Distance between X and Y minus distance in the gamma. Well, here it is X and Y. Should be careful, X and Y belong to the set of vertices of gamma. Okay, distance in gamma between X and Y is bounded by some constant C, and vertices, the set V in X is net. For some epsilon, epsilon can be 100, it doesn't matter, again, any number. So this is a much more hands-on definition of what is happening. And so this is the question. And so now once the definition is given, you're ready to start working and writing papers, because there are plenty of spaces around, and you can start asking which, of course, this definition makes sense only for unbounded spaces. If your space has a finite diameter, just put there 1 point and you are done, because I'm not requesting any specific values of constants. So a 1 point space is good enough for me. So we look at unbounded spaces. Now let me mention that, of course, you can look at bounded spaces as well. How you can do that? You can take a space and then start rescaling them, multiply distance by 1, 2, 3, 1,000, so on, and look for such graphs with a uniform constant. Is it just taking a union of these things, connecting them by segments of length 1, just attaching points, or just asking that you get a graph in each space and the bounds are the same? So the question makes sense for spaces of finite diameter as well, but I don't want to dwell on that at all, just to mention that this question makes sense. But so far I'm thinking about unbounded spaces. Of course, the real line is obviously approximable. You just put on the real line for R, you put just standard way, you put points at distance 1, and this is a perfectly good approximation whose precision, this constant C here, is going to be 1/2, right? That's it. Oh, well, no. Between these points, you just get exact distance. And this is 1/2 net. So these points is Z in R is 1/2 net. As I said, I'm not going to worry about what the values of the constants are, because after scaling, you can get anything. So, right. So the next question that comes in, and which is the main result I'm going to mention, is that this R square is approximable. This is a theorem by myself and Sergei Ivanov, that R square is approximable. And strangely enough, the proof of the theorem is not at all short. It takes like maybe 10 pages. Now there is a much easier theorem by the same authors, which is much easier theorem, that the same authors, that any Gromov hyperbolic space of bounded geometry is approximable. This is relatively easy. Even though this space may look a little bit more complicated, And what comes here is basically Morse lemma and standard distance estimates in negative curved spaces, in hyperbolic spaces. So it's delta hyperbolicity and the classic Morse lemma. So it's not a hard thing to do that. And also, what is there? Hall's lemma, Hall's marriage lemma. A little bit of combinatorics, but then it becomes not difficult. This proof, as I'm going to explain, even involves some Fourier series and funny things like that. Now, what we don't know, to just indicate the level of our ignorance, is that, first of all, open questions, and that's what I wanted to concentrate on, open questions. The first question is, does there exist any, well, let's say Riemannian manifold? It's not so important. Of bounded geometry, which is not approximate. Now, why I'm saying about it, what I mean by bounded geometry, okay, I'm running out of pages, so I need to add a page. Maybe what? Let me add like that. Okay, okay. Whatever I added is something like for elementary school, but probably doesn't matter. Okay, so what? Why I'm asking about bounded geometry? Because if I forget about bounded geometry, of course there are plenty of spaces which are not approximable. Let me just draw here a tree. It's a tree in R3. So here is, we are sitting in R3. I'm drawing a tree, and this is an edge of length 1. Then from here, I draw 2 edges of length 1. From here, I draw 4 edges of length 1. And I keep going. 8. And then I take not a tubular neighborhood in a matrix space, but a thinning tubular neighborhood. Which looks more or less like that. You take a tube around this edge, then you take a thinner tube here, you put a ball here, you drill holes, then you attach thinner tubes here, and you keep going. It's very easy to see that this thing is not approximable, because a graph, whatever graph you construct, it is going to have unbounded branching at this point. I mean, as you go along this thing, because we branch. But of course, it's not bounded geometry. So what I normally would mean by bounded geometry is say that injectivity radius is bounded by some constant bigger than 0. I wonder if I need anything else for this problem. I normally ask for curvatures to be bounded, but maybe even not that. Maybe what I want to ask, curvature sigma is bounded by some constant k, but even with this simple assumptions that just the injectivity radius has a reasonable bound already. So the major question is, are there any manifolds which are not approximable? And to explain how little we understand about this thing is another open question, which is directly related to that. Open question, is R3 approximable? I guess some people are smiling. I mean, how can you can do that for R2? What's the difference for R3? First of all, let me explain what are the difficulties for R2 and why it is not so trivial as it might seem. Indeed, first of all, a completely wrong thing completely wrong idea. Wrong idea. There are many wrong ideas now around in the world, so why don't I present you another one? You can just say, what's the problem with the plane? Just take the grid. Let's see, this paper is handy, and put lengths of vertices to be 1. And what you see here, well, you will see actually an L1 metric, right? It's going to be L1. Where do I put 1? Up or down? I don't know. Okay, L1 metric. Right? The distance between 2 points, as you compute it, you look at the length of the shortest path, which is just the sum of 2 coordinates. Well, absolute values, differences of coordinates. So it's L1 metric. And it's a reasonable approximation, means that it's a linear approximation. But of course, the error is not bounded. Well, here is, additive error. And I want to emphasize that. We want to additive error. If you look at this formula, which was at the very beginning, I was asking for the additive error. So the difference, it's not the ratio. For the ratio, it's a tangent cone or something like, well, whatever. It can be even square root of the distance, and the tangent cone would be the same. Now we are looking at exactly Gromov-Hausdorff distance. So it's, I want the error to be, so it's very different. So it's not an example. So this is a non-example. Furthermore, it's an exercise. Well, an exercise for those who know what is a stable norm of metric. Maybe I'll mention it very briefly, even though not so much time is left. I'm not sure even I'm going to speak about any other of open problems the time I have. But anyways, so an exercise on stable norms of Z to Zn invariant metrics. No periodic graph. Would do the job. Okay, so it's trying to construct a periodic graph, which is nice enough. Like this example, it is not going to work. Actually, the right formulation is the following: that for a periodic graph, it's the, well, okay, let me change it. The unit ball of the stable norm is, of course, convex polygon. Nothing like a circle. So the divergence is linear. Now, let me tell you what the stable norm is. There is a very old theorem of mine with an important lemma, which I borrowed from Fedor-Nazarov. And here's a theorem, which maybe you, if you never saw it, in all this kind of stories, it's quite important. If you have a length metric, which is Zn invariant with co-compact. A good model for you to think is that it's the universal cover of torus. This is metric D. Then I have to add a page. Then there exists, and of course, they're unique. It's immediate, a norm such that this norm, it's called a stable norm, such that distance between any two points, whatever far they are from each other, differs from the norm from them by no more than some constant c. So of course there is some constant c. So this is a stable norm. And then it is of course unique because if two norms they always diverge linearly, this is an additive constant, so you never can have two norms with this property. There is one, and when I told this result to Dmitri Burago, he went through 3 stages. The first stage was it absolutely can be correct. The next stage was it is interesting. The third, it should be obvious and much more generality. Well, still I don't know an answer for semi-hyperbolic groups. This is also true in proper reformulation for hyperbolic groups. If I have time, I will explain you how to formulate it for general group actions. But anyways, so we have no hope for working with periodic graphs. So we need to somehow gently moving away, somehow wiggle the graph out to cancel errors and so on. And here you understand why the function, my favorite function is going to be absolute value of x. The function from r to r plus. It's going to be my favorite function. Why I'm going to be so excited about this function? Because locally, let's imagine that I have a large piece of my space, in this case my plane, because I don't know what to do with R3. And on a large piece of art, I put something periodic. Then on this scale, if I measure distances, I see some polygonal norm on this thing. So a unit ball looks this way. And of course, I'm not very happy. So what I want to do, go into another piece. So near each direction, which goes here, what I see is after some change of variables is the absolute value of distance. If I take the dual, of course, I'm going to go to the dual norm to have proper addition of norms, but I would have kind of absolute values. So what I want to do is I want to make a sort of a quasi-crystal, but not exactly quasi-crystal. This quasi-crystal has to be selected very thoroughly, but rotating those norms so that I get proper cancellation of errors. So when I go to, in this region, it is like that, then I'm going to move this corner in this region somewhere here. It's a different direction. Then I move it somewhere in between so that I do addition. I don't accumulate more than an additive error. That's where the key point lies. Now I would be able to do that only around some sector of directions. So we do that near one direction. And this is not a big deal because there is an easy trick. You can take a multi-layered graph. Once you've done this around one sector of directions, so this is a copy of your plane, R2, and you've done it in this sector of directions. Now let's increase distances in all other directions. So it will be very uncomfortable to go there. Then you take another copy of the plane and handle another direction. You keep adding copies. You put yet one more copy on top and handle another direction. You take finitely many of them. And so you badly increase badly. Okay, in the outside of those segments. And then you make connections. That. You make connections, just connect corresponding points vertically by segments of length 1. There are finitely many copies. We are working up to a finite constant. Then whenever you want to go between 2 points, obviously you go to a copy where your direction is in the corresponding sector, travel through this copy, and then return back. Because on other copies, going in this direction is very expensive. So you just lose a constant of going between copies back and forth. Other directions are unprofitable. So you handle one direction, and then for handling one direction, you need to somehow move corners of your polygonal norms. So the plan is, is to move corners of our polygonal norms in such a way that they add up to a circle with bounded error. This is our plan. And here we go into a completely different area, which mixes analysis and dynamical systems. I think the questions are going to be at the end because, a possible question could be, what are the open problems you have? But anyways, since I have like 6 minutes left, probably, yeah. So let me ask you the following question. I have an interval 0, 1. And I want to put points x1, xn uniformly distributed. The best choice I want to do. What does it mean? It means that if I count the number of points of this set, let's say it set xn, xn intersect with some interval I, the number of points should be, of course, length of I times n. Well, and then error term. How bad can this error term be? Of course, just put them as everyone would do. Here, you put them at equal distances, right? And then the error term is no bigger than 2. It's a triviality. You can just lose 1 point at each end of the interval. So it's very easy. However, you ask another question, which turns out to be a way more sophisticated. Now you have a sequence, infinite sequence, xn, n equal 1, 2, goes to infinity. Well, infinity is not included. We're not in the calculus class. And so, and I want to do the following thing, the same for any truncation, for any xn, n equal to 1 to some number n. And I want to ask the same question. So it's in dynamics. I don't know in advance how many points I would have. And at any point, someone can say, stop, and look how good your approximation is. And that was a story, a quite long story. Probably the key people who I should mention here, among key people at least. I don't want to kind of disregard other achievements, but probably it's Schmidt and Ross. There are books written about that, showing that you can't do a constant at all. There are estimates how bad that could be. And I think that the estimate is something like log n instead of this 2. Here you see 2. You see something like probably log, maybe it's even better than that. Probably, perhaps log n maybe even log n, but definitely not a constant. Now we are solving a little bit different problem. It may seem to be almost the same. Let me remind you, the formula was number of points of the intersection of my set xn with the interval I is going to be length of I times n, right? The way I can write that is I can put a delta measure on each xi, the point, and then I just can integrate. So this is my measure delta, and I integrate delta over the interval I, and it's going to be about n times the length of interval. Instead of a delta measure, I want to smoothen it. And instead of that, I look at the function which is distance from xi to x. And look at the sum of these functions from 1 to n. And what I want approximately to be, again, what I expect, n times the length of the interval. And surprisingly enough, the answer here is that you can do a bounded error. And in the remaining minute, I would just formulate a theorem, which is a key lemma here, which requires some Fourier computations. Well, at least the way how we can do that. Fourier computations. It says the following. Let me say yeah, I have a function phi from 0, 1 to non-negative numbers with some boundary conditions, with some 3 linear conditions. I'll tell you, I don't want to write them, 3 obvious linear conditions. Let's say it's C2. And of course, I want it to be convex. Then there exists an infinite sequence AIs such that. So that's a lemma, which is of key importance here, such that if you look at the following function, sum of absolute values x minus AI, you subtract from that from 1 to n times phi of x. There is this constant c, as always, it's bounded by c. So any function you can get as average, well, it's much better than the average. A much easier statement would be if I divide everything by n. I don't divide it by n. It's still in this form. So it's much stronger form. If I divide it by n and say that it is bounded, that would be kind of a much easier statement. No, it's an additive error for all n terms. And the sequence is infinite. I is from 1 to infinity. Right. So there is this approximation lemma. And from this lemma, for this function, of course, you're going to take the circle. This is, you want to approximate by corners of your polygons a circle. And so this is what works. Where we fail in R3 is when instead of distances to points, you need to take distances to lines or to points in R2. And already we don't know an analog of this lemma. And what are obvious linear conditions? Well, first of all, convexity. Well, of course, I'm adding convex functions, distances to points. So I'm going to get something convex. No way I can get something else. Now, on the right hand of the interval, all these functions have derivative 1. So this phi has to have derivative 1 on the right hand. On the left hand, it also has derivative -1. And if you take the value of the middle, it's the average of the two. So 3 trivial conditions on this function. And I am out of my time already. So I stop here. I didn't get to any of open questions on my list, but at least I think I explained you the flavor of this specific problem. But it's a bunch of open problems. You can ask about the approximability of R3, even of a paraboloid. of a sphere in a reasonable sense. You scale spheres and you ask if you can approximate it with the same constant for larger spheres. Take your favorite spaces. I already took away from your hyperbolic spaces with boundary geometry. But take your favorite spaces for boundary geometry and you have plenty of work to do. I stop.
Okay, I suggest we unmute ourselves to thank Dmitri for a wonderful talk. Right, if people have questions, please, or comments, please go ahead.
I have a question. The general question is if, you know, in these approximability questions, could randomness ever be of help, or if people ever tried to use randomness? So, I mean, maybe to be more specific, if you're trying to approximate the plane, I guess, which we know you can do, but you know, if you divided it up into unit squares, you couldn't take the, you know, the edges on the boundary of each little square as you explained. But what if you know, chose 20 random points, you know, from each square and then assigned?
Henry, first of all, if you just do randomness, then with some probability, somewhere you will see large additive errors. So, but what we do using Fourier series here is to do whatever stupid it sounds, controlled randomness. So it's indeed kind of a rather random sequence, but such that we still control it and it cancels. So we don't see a lot, because if you just, okay, it's of course a natural idea just to take, say, random values of distances between, say you take the standard grid and take random values between 1/2 and 2 and hope that things are going to be round. And probably with probability 1 on large pieces, this thing is going to be round.
Yeah.
However, as a graph, to answer this question, it does not work, because there still would be large pieces if you take it random, where you will see just standard, say, L1 metric and such, so you will see huge deviations. So you can't take them just random. What is controlled randomness through, there are Diophantine numbers and such which are involved in this Fourier series to make them sort of random.
Very cool. I'll ask another question. So you mentioned this problem of on the unit interval, you know, choosing points, and then you don't know when you're going to be told to stop, but when you're told to stop, you want the points you've selected to sort of, you know, approximate the uniform measure in some sense. So, I mean, does this work by Schmidt and Ross or others? Does this relate to the golden ratio? I mean, sort of choosing points?
Yeah, that's a very complicated story, how you choose them and how you prove that you can choose them. I saw a book which is like that thick, discussing these issues for just how to choose dynamically random, dynamically uniform sequence. So it's another question could be, you can ask for intervals from 1 to n, you can stop anywhere. You can ask for an interval from m to n somewhere, it's a different question, right? So there are many issues coming out from there, and there is quite a bit of complicated mathematics, how you do that dynamically. As I said, for the static thing, of course, you just take points at equal distance from each other, and a school kid would immediately tell you that this is basically the best you can do.
I see. So it's more complicated than this golden ratio. If you sort of choose points according to, you know, this golden ratio and then round mod 1, that maybe has multiplicative error, whereas you're asking for additive error.
Well, see, this is quite difficult. Let's see what is happening. Let's say this is my interval 0, 1. Where do I put the first point? Naively, I want to put it in the center. Okay, let me try that. Then on the second step, I am already not very good, because I have to put my point somewhere. The next point goes somewhere either here or there, and the density here is completely different from there. So maybe for the first step, I should be smarter. Maybe I should put my point somewhere here, so that I'm not so good at the first step, but on the second step, I can choose my point here. But then what do I do on the third step? My point lands in one of these intervals, and then the density on this interval is going to be much higher, and this density here is much smaller. So maybe I should prepare it even better, but then the first step already is not so good. It has not. I mean, it's a very tricky question.
Right. So controlled randomness again.
Yes. Yeah. It's how do dynamically, and it was a huge surprise to us. A great harmonic analyst, Fedor Nazarov, he first didn't believe that this could be possible because all we did is we substituted characteristic functions by absolute value, by distance to a point. And this kind of regularization, a little bit of regularization, tells you how to put the points. But again, the strategy comes from some Fourier series and some continuous fractions for specific numbers. So I can't tell you kind of as a, it's not a strategy for a chess game. It's how you choose these things comes from some black box in a sense, how you choose these points. But if you try it, and this is what these books by Schmidt and Roth, I remember a book by them. Yes, how you choose these points, even the question very well, okay, since you're looking up to a bounded error, of course, the first several ones do not matter. But once you get where it matters, you see exactly the same problem, where to put the next one. Do you want to put it here, or a little here, or where you shift it so that, I mean, it's a brain twisting question.
Thanks.
Are there any more questions?
I'll ask another question if nobody else does, which is, I'm definitely a non-expert on these approximability questions. My first instinct might be, I might try to prove that R3 is approximable, or, other manifolds of bounded geometry are approximable. I mean, do some experts agree with me, or are many people trying to prove that spaces are not approximable, like R3?
Well, the problem is that I do not know any tool, unless the space has unbounded geometry, and then the tool is just by bare hands and immediately. But once it has bounded geometry, I don't know any criterion which would tell me that it is not approximable. I have no idea what to prove to say that it is not approximable. So far, the existing proofs are constructive to give approximability. So in R3, if you look at a stable norm, what happens for a periodic graph, you see a polyhedron. You start adding distances coming from polyhedra. So instead of adding absolute values like near vertices of polygons, you start adding distances to lines and conical functions, distances to points near vertices. And you need an analog of this theorem. And this does not work. This Fourier series type stuff does not work for that case. But I have no idea what condition we can prove to say that the space is not approximable. The problem is that it's like, a slippery snake. You don't know how to grab it at all because it's absolutely slippery. What to prove to say that the space is not approximable? How on earth the proof at all can go? So that's why this is for me a big puzzle. And because of that, either we find so some time ago, for instance, we were working with Bruce Kleiner on the following question. You have a separated net with Bruce Kleiner. I think we still have 4 minutes out of 50, right, for questions with Bruce Kleiner. And also, actually, there's also Kurt McMullen. On the following question, you have a separated net. Oh, it's a Delaunay net in R2. Is it by Lipschitz to the lattice? And there was a big struggle around this question, and a solution. We needed to show that, well, you can produce a lot of nets which may, well, on one on the one hand, it's just the same kind of distributions, points are within distances from 1/2 to 2, for instance, doesn't matter. So why can't we send them by Lipschitz to the lattice to normalize that? The question was asked in two respects, by Furstenberg for Kukutani equivalence, where this comes as a return times for Z2 action in dynamics, and by Misha Gromov for the very definition of quasi-isometries, where spaces are quasi-isometric if they have separated nets which are by Lipschitz. So the question is, does it matter which separated nets to choose? And we've proven that this may not be the true. We found an obstacle which is intermediate uniform density, which gives you a continuous function C from 0, 1 to, let's say, 1/2 to 2, continuous, and phi. Phi is not a Jacobian of any f. F is a Lipschitz one. This question itself was asked by late Jürgen Moser. And this question comes from Furstenberg and Gromov. And still, we have artificially constructed nets for which our invariant, which is some kind of limiting intermediate density, works. But we don't have any general tool. So there are many naturally coming functions for which we don't know if they're Lipschitz, Jacobians of Lipschitz maps. I will finish this talk. Well, I'll leave half a minute for questions. Let's say gamma 1, gamma 2 are co-compact in a G, which is a Lie group, with a left invariant metric as usual. Is it true? G1 is by Lipschitz to gamma 1 is by Lipschitz to gamma 2. Here, no density works. They're both uniformly distributed, nicely uniformly distributed in the group. Can you just identify them in a by Lipschitz way? It's a shocking problem. For most of groups which we know, we find such thing. So there should be some rather complicated, mysterious Lie groups and lattices in them. This question is about the same type. We do not understand any abstraction which we are going to prove to say that when you prove that something doesn't exist, you usually prove that something exists which obstructs non-existence, right? Here we don't know what to prove what exists, so that because of that, this does not exist. We have no idea how in principle a theorem that space is not approximable can work, other than for very specifically made examples where it's just obvious from the construction of space. So I am out of time.
I have a very quick follow-up question regarding the description of R2 being, and then separated nets in R2. Does anything change if you work with on the two-dimensional model space with constant curvature -1?
Oh, I said that. If you have any bounded geometry hyperbolic space, it is approximable. It's easier than that. So the hyperbolic space in any dimension is approximable.
Oh, but I meant the question of separated nets, that one.
Or for separated nets,
yeah,
yes, the answer is funny. And for separated nets, the theorem, there is an easy theorem, relatively easy theorem. Easy theorem. I think it's due to White, spelled not a standard way, that in hyperbolic space, every two separate nets are by Lipschitz. Yes. So this is known. This is known, but see, it's not so surprising. As you go on, so you start building this net, this map. Not only they are by Lipschitz, but actually there is bounded distance map between points. You go from a sphere of radius n, and you go to a sphere of radius n+1. You add about the same number of points as you already had So it's not an Euclidean space. In Euclidean space, the number of points you add is just it's a polynomial, so it's next degree. Here you add about the same number of points. So you have plenty of points to connect to where you map them. And for additional points, again, you have enough points to connect to. Formally, this is done again through the Hall's marriage lemma. By the way, for the group question here, let's say that co-volume gamma 1 is equal to co-volume is gamma 2. Then true. So in many groups, this answers the question. Why this is true? Let me just explain you a proof. Let's take the fundamental domain, any fundamental domain for gamma 1. It's a fundamental domain. Here is a little piece of the talk where I'm going to give you a complete proof. And a fundamental domain for gamma 2. Then shift them and make a link G1 belonging to gamma 1 and G2 belonging to gamma 2 if, well, fundamental domain is F2 and this one is F1. So if G1 of F1 intersects G2 of F2, well, maybe I take interiors, whatever it is non-empty. So I make a link. And now the conditions of the Hall's lemma, every collection of elements from gamma 1 connected with at least n elements of gamma 1 connected with at least n elements of gamma 2, because you can't cover the images of this fundamental domain by a smaller number of things. They are of the same area. And the other way around. So there is a bipartite graph, which you can use as a graph of the map which you construct. And this is a finite displacement map, which on separated maps is automatically by Lipschitz. It's a complete proof.
Thank you. Are there any more comments or questions? All right, so thanks again for beautiful presentation, a beautiful talk. So I'm going to stop recording, and if people want to stick around for a few more minutes, please do.
Okay, thank you.